This simulation shows which path is the fastest trajectory towards the final point only from the gravitational force. And so in this video, we'll be discussing about how do we solve these types of problems? How do we solve such optimizing problems? But before we get started, please go ahead and check the notes in the description as well as the timestamps for you to skip through just in case if you want to understand only a certain topic throughout this entire video. So before we get started, we need to understand why do we need to understand calculus of variations. Or especially in here, we need to try to understand how to solve the calculus of variation. So, so one of the most essential thing is Lagrangian mechanics. So Lagrangian mechanics is basically a different perspective of the Newton's law. So it consists of two different things. The first is the Lagrange's equation, and the second is the Hamilton's principle. So these two things are basically scalars, and these two scalars are related to energy, and minimizing this function as a function of energy here, we can get the trajectory of the motion very fast. So that's one of the key things in terms of the classical mechanics. Another thing is that if we consider about how light moves, it always follows the Fermat's principle, where it basically means that light travels at the fastest path. So it's not the shortest path, it's always the fastest path. And so before we continue on, make sure to like and subscribe so that you don't miss any video that I upload in this channel. So let's write down the problem that we need to solve. So the problem is, let's just have j, which is just the integral of the function yx, y derivative of x, and x dx, and you want to find for what yx would j be local min or max. That's basically the problem. So solving this straight away seems to be impossible. So we can try to think of a solution that should exist. And one such solution would be if we consider that y0x is the solution, we can say that y alpha x is y0x plus some error, which is a function of x. So this error here is gonna be 0 on the pinpoints, but in between it could be varied. So let's say this is the actual solution, and we have some variations, which is not exactly the minima or the maxima. So we can just rewrite the problem into j alpha is the integral of f y alpha x y prime x x dx, and we want to find where's the local minima and maxima. And because the j here is a function of alpha, this would mean that we could actually just say that the partial j over partial alpha to be 0 when alpha is 0, because when alpha is 0, this is the exact solution. So trying to solve your problems by only using this idea is not ideal because you need to do guessworks in order to solve the problem. So instead, we can try to develop a formulation such that we can figure out what is the solution of the problem. So we'll be introducing the Euler's equation. So we'll prove Euler's equation first. So if we try to solve what's the partial j over partial alpha, this would be the integral from x1 to x2 of partial f over partial x, no, partial y, of partial y over partial alpha, plus partial f over partial y prime over partial alpha, and then plus the partial x over partial alpha, which is 0. So we only use the chain rule such that we can obtain this following equation. This should be 0. And something to note is that you could determine what's the partial y over partial alpha. This is eta. And for this is d eta over dx that you can actually prove straight away. So this would mean that you can rewrite this as partial f over partial y of eta plus, and in here, because it's partial f over partial y times partial eta over partial, no, d eta over dx, we can see that this looks like a chain rule. So we can just use the chain rule. It's gonna be plus the second term, in which if we see here that it looks like a product rule, so we can just express this as partial f over partial y prime of eta, evaluate that from x1 to x2, subtract this by the integral of x1 to x2 of eta d over dx of partial f over partial y prime dx, like so. So something to note is that if you try to put x1 and x2 into your eta, this would be 0 because we know that at the endpoints the error should be 0. So what we obtain is this equation here, and this must equal to 0, or x1, x2 of partial f over partial y minus d over dx partial f over partial y prime, multiply this by eta dx equal to 0. Now this must work for all eta, otherwise it's not a minima or a maxima. So we need to have this coefficient here to equal to 0. And this is what we call as the Euler's equation. Subtract that by d over dx partial f over partial y prime is equal to 0. So you just need to solve this problem and you can get a solution which is either a local minima or a local maxima. So by only using this equation, we can actually solve lots of different types of problem. One of them is the brachistochrome. This is the minimum time. So you want to find a trajectory that has the minimum time, trajectory with minimum time. And one of the example is the simulation that I've shown before, where the solution here actually turns out to be a cycloid. So if you want a fuller derivation, you can check the shorts shown here. Another type of problem is the soap film problem. So the soap film problem is a interesting problem as well, where you need to minimize surface area. So if you have, let's say, two different loops, and then let's say you soak this with soap, there will be a bubble forming, and you want to figure out what is this shape that is minimizing the surface area of this revolution. And it turns out that the solution is the catenary. So later on, like we'll be introducing how do you find the minima if there's constraints, but to show this geometric object physically, this looks like a something like this, where if you have a rope pinned between two different points, it's dripping down. While for the cycloid, it's a point in a sphere that is rolling. So it would be something like so. So another problem that you could solve is actually the geodesic. The geodesic is basically the minimum distance. So for the geodesic problem, normally the solution is just a straight line. Sometimes if let's say you have a hilly surface, you can't you can't really go uphill and downhill again, otherwise it's going to be increasing your distance. So you might need to turn in some circumstance in order to minimize this distance. So there's another way for us to write the Euler's equation, and this is where the second form comes in. So the second form starts with the definition of df over dx is just a partial f over partial y of partial y over partial x, or just y prime, plus partial f over partial y prime of partial y prime over partial x, which is basically y double prime, and lastly, it's partial f over partial x. Technically, all of this is d because technically our function is just a function of x. So it's totally fine. So now if we try to write this down again, this is partial f over partial y of y prime plus partial f over partial x. And for the second term here, I want to expand this. And this is because that y double prime is something that we don't really denote. So maybe we can just express this into another type of equation. And something that I will point out in here is that we can use the product rule of the derivative. So it will look like the d over dx of partial f over partial y prime times y prime. And then you just need to subtract this by the d over dx of partial f partial y prime times y prime, like so. So if we try to group this together, you could see that this partial f over partial y and this d over dx partial f over partial y prime is going to be 0. So therefore, we can get d over dx times f minus partial f over partial y prime dot times the y prime is gonna be partial f over partial x. And if we consider a very specific condition where partial f over partial x is 0, or basically your function only depends on the y as well as the derivative of y, we can just write this down as f minus partial f over partial y prime times y prime is gonna be a constant. So if you can see here that there's no more d over dx anymore, everything looks much more smoother. So sometimes using this equation would also help you to solve those types of problems. So in here, I want to emphasize that solving calculus of variations require lots of practice. And so in order to do that, you can get the practice problems just by copy and pasting the entire description and send it to your favorite AI so that they can make practice problems tailored for yourself. So we mostly discussed about a single variable, or precisely it's a variable that depends on x. But there could be other components as well. So this is where if we try to consider multiple different variables, we need to consider what is the Euler's equation for this multiple variable. And it turns out that it's quite simple. And this is because if we actually try to rewrite the same thing as before, the partial j over partial alpha, this is going to be the integral of, well, first we have the y components, which we got that to be eta times partial f over partial y minus d over dx partial f over partial y prime, right? So if we try to index each of these and make it into a sum, it's basically denoting each of the different components. There's the y, there's the z, and so on. And so because this condition should be satisfied for all eta I, this would mean that partial f over partial yi minus d over dx partial f over partial yi prime has to be 0. So basically, Euler's equation always works as long as there's no constraints. But what if there is a constraint? So to solve this, we will try to consider a constraint where there is two variables. So two variables is the easiest, and then I won't really prove for the higher variable case, but it can be shown that it will always work. So let's say g of xyz is gonna be 0. So we can rewrite the partial j over partial alpha first. So it's the integral of partial f over partial y minus d over dx partial f over partial yi prime. Multiply this by eta of y plus the partial f over partial z minus d over dx a partial f prime, no, sorry, partial f over partial z prime of eta z dx, like so. Now something to notice is that this eta y and the eta z is just the partial y over partial alpha, right? Yi technically. And a way for you to get this partial yi over partial alpha is also from the constraint. So we can rewrite the constraint to be the, so if we take the partial over partial alpha, 0 is going to be partial g over partial y times partial y over partial alpha plus the partial g over partial z of partial z over partial alpha, like so. So what we see here is that this is basically partial g over partial y times the eta y plus partial g over partial z times the eta z have to be 0. So if you now try to plug in the eta y's, it's going to be the integral of partial f over partial y minus d over dx, partial f over partial y prime of, in here it's going to be so there will be only partial f over partial z minus d over dx, partial f over partial z prime, multiply this by the negative of partial g over partial y over partial g over partial z times eta y, like so. Yeah, so this is what you obtain, and this has to be 0, and so this means that for any eta y, the inside should be 0, meaning that partial f over partial y minus d over dx, partial f over partial y prime times partial g over partial y inverse must equal to partial f over partial z minus d over dx, partial f over partial z prime of partial g over partial z inversed. And this is something which we call as lambda. So if you now use this idea, we can build it up into this equation. Partial f over partial y subtracted by d over dx, partial f over partial y prime, plus lambda of partial g over partial y. And this has to equal to 0. So what I wrote here is the same thing as the one at the top, but in here we use the lambda here. But if there's multiple different constraints, we can just put this as the sigma of the j for each of the gj, and then for each of the yi's, like so. So this is the condition for the local minima or the local maxima. And you must also remember that another boundary condition is g of x and yi should be 0, something like that. So only by using these two equations, you should be able to solve any type of calculus of variations problem in terms of the multivariable as well as the one with the constraints. But there's also another type of constraint. Instead of having a function that is constant, you could say that there is a functional that is constant. So from a to b, there's this function which has to be the value k. So it can be proven, like the Euler's equation could be proven for this particular case, but I won't show it here. But basically what you're gonna solve is just the extrema of the integral from a to b of f plus lambda g. So lambda in here is also another constant, or the Lagrange multiplier. So technically what you're trying to solve is just the partial f over partial y minus d over dx of partial f over partial y prime plus lambda of partial g over partial y minus d over dx partial g over partial y prime. So one example of using this type of equation is the Dido problem. So the Dido problem is basically if you have, let's say, a fixed amount of string and you want to maximize the area, you use this type of constraint and using this type of Euler's equation. So the last thing that I want to discuss is how do you actually write this problem in terms of the mathematics. And this is what we call as the delta notation. So you could basically just write down the problem to be the delta of j as 0. But then there's reasons as to why we can write it as so. So we will just write down the partial j over partial alpha, and we'll multiply this by d alpha. So it's the integral of partial f over partial y minus d over dx of partial f over partial y prime. Multiply this by the eta x, which is the partial eta, no, sorry, it's partial y over partial alpha. Multiply this by the alpha and dx, like so. So we can actually just cross out the partial alpha and the d alpha. So this is just delta j, and this is equal to the integral of partial f over partial y minus d over dx, partial f over partial y prime of dy dx. So the d in here is technically the delta because we are using the notation for the small change of alpha, there's the small change of y. So that means that we can actually extract some informations, which is the delta j is the delta of this partial f over partial y minus d over dx, partial f over partial y prime dx. And this have to be 0. So basically what we show is just a different notation in writing the calculus of variation problem. So basically what we show here is that this is basically how do we express the problem. So it's the same thing as writing the delta j as 0. It's basically the same thing as just use the Euler equation to solve the problem. And so this is the end of the video. And I know this is a skim through of the mathematics for the classical mechanics. And so if you want to take the practice problems, you can go ahead and copy paste the description and send it to one of your favorite AIs and try to solve those problems. And if there's any problems with those questions, feel free to reach out to me so that you can understand the mathematics behind the physics in a much more deeper understanding. Thank you very much, and I will see you on the next video.